Very much of an achievement, but to me that. Anyway, I interpreted my instructions for today as sort of providing something light and fluffy and not too mathematical, no sort of proofs or anything like that, or even stated theorems, just sort of an hour's entertainment of some kind. So it'll be fairly sort of philosophical in character rather than mathematical. I just want to I just imagine that there's a debate about whether computers will ever be able to do interesting mathematics, and I'll present my side of the debate and nobody will get their chance to present their side. Although actually part of the reason I chose this topic was that John Toland suggested it because he'd seen that I was going, so to speak, head to head with Roger Penrose in a pair of public lectures for the LMS. That's in a couple of weeks' time. So I don't recommend going to that unless you just want to go and see Roger Penrose, because you'll have. I won't be saying exactly there what I say here, but it'll be pretty similar. So let me start by just mainly sort of saying what I'm not talking about. So there are certain things that computers can do that are very helpful. We all know they can do those, and they do remove some of the work from mathematicians, but somehow it's not the fundamental question. So we know that they can do lots of very, very quick calculations, and that these quick calculations enable us to do more in our research than we would be able to if we didn't have that help. There are several different types of examples. I've listed a few there. So one obvious one is where you have a problem that reduces to a finite check, but a very large finite check, something like the four-color theorem, for example. But there are several other examples. Sometimes we can use the computer to just do experiments. You know, we're interested in the zeros of the zeta function, so we can start looking at a large number of zeros of the zeta function, see whether they lie on the critical line and things like that. And a lot of very interesting work has been done of that kind. That's related to the third point. If you do a lot of experiments, it often brings out patterns. Maybe you draw a graph or something and you see something in the graph that you would never have suspected if all you could do was hand calculations. And once you've got a pattern, you've got something to prove. And proving a specific statement is much easier than sort of proving a very, what am I trying to say? If you want to say what goes on here, it's much easier to answer the question, is this what goes on here, than just the original question, what goes on here. And if you've got a computer that can provide you with lots of data, it can provide you with concrete conjectures to test. OEIS, I expect you all know, but that's the Online Encyclopedia of Integer Sequences. So that's a very nice way of generating conjectures. You're working on something, you generate some sequence of numbers, you go off to the Online Encyclopedia of Integer Sequences, you see if that sequence exists there. Very often it does, and it's been generated in some completely different way. And there is a ready-made conjecture, or at least interesting problem. Well, the conjecture might be what I've just done is connected in some way with this thing over here, because they generate the same sequence, or they appear to generate the same sequence. And there are some very fascinating bits of mathematics that have been, or conjectures that have been discovered and sometimes proved in that sort of way. EDP is a less obvious acronym, and that stands for Erdős discrepancy problem. That was a problem that I and several other people worked on online, and we found that generating data and staring at it enabled us to come up with all sorts of sort of partial conjectures towards the whole problem, facts that were clearly true that we wouldn't have guessed without the help of a computer. And another thing that computers are obviously good at is simulation of various things. And again, if you're a fluid dynamics person in some areas, there's a whole branch of computational fluid dynamics. They can find out all sorts of things with the help of computers that would have been out of the question in the pre-computer era. And none of that is what I really want to talk about. What about some things that people would think that computers can't do? Some people would be fairly certain that they can't do them. I will just stick with the rather safer, cannot definitely do. Although actually, even that I don't think is a totally safe statement. So somehow there's a feeling that with a computer you have to have the ideas and then the computer is just your sort of slave that works out the ideas. But the computer itself is not going to have the interesting ideas. You can, so that's something that a lot of people would say. They can't be creative. When they're doing things, they don't know what they're doing, they just do it, and still less do they have the faintest idea why anyone should be interested in what they're doing, and so on. So that's the kind of criticism that's leveled at computers. They're nice as slaves, but they're fairly stupid. Their one virtue is that they can do things fast. And let's move on to some slightly more sophisticated arguments. So those are just bald assertions. I mean, maybe they're not true, maybe they are true, and that's not exactly an argument. But some more serious arguments against the idea that computers might be able to do mathematics. So I think one very influential argument, and one that a lot of people like, is the argument that the problem here is a mathematical statement. Is there a proof of that mathematical statement within some proof system? Is well known to be equivalent to the halting problem. Therefore, there is no algorithm for solving it, and to many people that looks like the end of the story. Why is it not the end of the story? Well, there's a very simple counter to it, which is we're not interested in proofs that are over 1 million pages. I suppose that maybe you could prove abstractly that there exists a proof of over 1 million pages. There are one or two situations like that, in which case the proof that the proof exists would not be 1 million pages. So I think that sort of somehow doesn't count against this. So there's some upper bound at any rate. We're certainly not interested in a proof that would take longer than the age of the universe to read, for example. So there's some upper bound, and the problem here is a mathematical statement: does there exist a proof of fewer than 10 to the 10 to the 10 symbols of that statement? Is one that you can solve with an algorithm. The algorithm just simply writes out all strings of length 10 to the 10 to the 10 and checks to see whether they are a proof of the valid statement. So that problem is not equivalent to the halting problem. I sense a little objection to that strategy in people's minds. So let's move on to argument 2. Okay, so the real problem is perhaps better rephrased as: here is a mathematical statement. Does there exist a proof of that statement that uses, or of length at most n, whatever you define your length to be? And so we know there's an algorithm for that, which is, as what I just said, you just check through all strings of length n and see whether they're a valid proof. But that takes exponentially long in the length of the string, and we don't really regard algorithms that take exponentially long as practical, and they're certainly not going to, if somebody said, I've got a computer program that can do maths, and then you discovered that all it was doing was an exponential search through strings that it then checked, you wouldn't be very impressed. So what on earth could one argue against that? Well, there is a very strong argument against that, which is that is not the problem that's interesting. The problem that's really interesting is, to me anyway, can computers do what mathematicians do? Now, if you give a mathematician an arbitrary mathematical statement and then say, does there exist a proof of this statement that uses less than 500, or less than 30 pages, let's make it slightly more concrete, there's absolutely no reason to suppose they can do it. And if you want to, maybe just to make that clearer, supposing I gave you a graph that had been carefully judged to be a difficult case of the travelling salesman problem. So I gave you a graph and said, is there a path with distances between the vertices, and said, is there a path through these vertices of total length at most 1,000 or something like that? There's no reason to think that you as a human have some magic ability that would enable you to answer that question quickly, where a poor old computer, because it's just a computer, couldn't answer it quickly. So in other words, we're not just answering, when we do mathematics, we're not just answering arbitrary instances of NP-complete problems. We're answering very specific sorts of questions. So we definitely sort of have a very strong feeling when we do mathematics that some questions are more interesting than others, or some questions, though very interesting, are completely intractable, whereas other ones there's some hope of making progress, all that sort of thing. So it's clear that what we're doing is not looking at arbitrary mathematical statements and trying to find proofs. we're looking at a very, very small subset of the set of all possible valid mathematical statements. And I'd go even further. We're looking for a very, very small subset of the set of all valid proofs. It's conceivable that there's some very nice, well-known conjecture that has a completely miraculous proof that would not be findable, except, and if you say if you read it, you'd have absolutely no idea where the ideas came from. So maybe there are proofs that are so sort of weird that the only way of finding them is by just brute force search through proof space or something. But if so, there's no evidence that we're ever going to find those proofs. So there we are. I think I've said enough on that one. So we have to work a little harder if we're going to show that computers can't do mathematics. And in particular, I would maintain that if you hold the view that computers can't do mathematics, then implicitly you are saying that there is some sort of boundary between what computers can do and what they can't do, and that there are some problems. Well, let me just that I've called here irreducibly difficult. Let me just give a sort of sketch, quotes, proof, unquotes of this fact. So it's an induction argument. So if it's not true that there is an irreducibly difficult problem, then whenever you've got a problem, you can somehow think about it for a while and reduce it to, say, a bunch of easier problems, which is what we usually do when we solve math problems. So if you can always do that, then assuming that the notion of is easier than is sort of well-founded or something like that, which seems a very reasonable assumption, then at some point you're just going to reduce it to problems that are so easy that you can solve them. So the only way of defeating that argument is to demonstrate that at some point you get a problem that can no longer, well, that a human can somehow magically reduce to easier problems, but no computer ever could. That would be, I think that's a very strong claim that you have to make if you want to argue against computers in this. I see here a parallel with arguments like evolution can't be true because the eye would never have evolved, things like that. People say the eye is an irreducibly complex organism and a sort of partial eye would be useless to the organism that had it. That's the fallacy, of course, because it's not true. Just a sort of very vaguely light-sensing thing could be useful to the organism that had it, but that sort of argument has been advanced and squashed in the case of evolution. And I'm going to try to present some sort of things a bit like that here. It's not that easy to talk about a sharp boundary for one reason, which is that because you can do searches by brute force, I can't say that you could never ever find such. There's no chance of saying that you can't ever find a proof. What you have to say is something more like there's no way of efficiently finding a proof, or it's very, very unlikely that a proof would ever be discovered because the quickest algorithm would take exponentially long, or something along those lines. But you can do that, so let's not worry about it. So let me think of some kinds of reasons that people might advance for the existence of this supposed boundary. One thing that people would often say is the computer can only ever do what you tell it to do. So maybe you can program a computer to solve some nice class of problems. The moment you step outside that class, the computer just is completely stuck. There's a sense in which that's sort of trivially true, because you can define the class of problems to be precisely the set of problems that the computer can solve. But I think it's meant in a slightly stronger sense than that. Another thing that humans do often, supposing we get stuck on a problem, we don't just carry on trying to do the same thing over and over again. Instead, we have this sort of ability to jump out of what we're doing, to step back and say, what's going wrong here? Why am I failing to solve the problem? And we sort of jump up several meta levels as we proceed. And that's something that's not obvious how one would get a computer to do. A very characteristically human ability that is extremely useful in mathematics is pattern recognition and spotting of analogies. We often, when we're working on a problem, we say, that reminds me a little bit of some other problem that I was working on 2 years ago, and then you look at it and the connection is not always all that clear. You having been reminded, you say, well, what would be the analog of this that works in this proof over here? And it's not obvious and you have to think for a while. So given that the analogues are not, there's not a sort of obvious one-to-one mapping between a concept here and a concept here, you can ask how on earth did you spot that there was a connection in the first place? No obvious, it's not completely obvious how one would program a computer to spot sort of vague, well, that brings me on to my next point as well. In general, how do computers deal with vague ideas, which are very important to humans when they're doing maths? Another thing that's very important is visualizing. It's, again, not completely, computers are much happier with pushing symbols around than they are pictures. And also another very interesting thing about the way humans do maths, which we've all experienced in our teaching. If you're teaching a course, you can set a few problems, and if somebody conscientiously works through those problems, what they end up with at the end is not just the ability to solve the problems that you've set them, but the ability to solve a whole lot more. Somehow people draw general lessons from specific problems in a very interesting way, and again, it's not obvious how computers can do it. So I now want to turn to the question of, this is in particular, I want to argue that computers can have ideas. So here's a problem that I think probably everybody will be familiar with. I hope they are, because it's a terrible shame to give this problem away, or give the solution away to people who are not. So this is the famous problem. You have a chessboard with two opposite corners removed, and you'd like to cover it with dominoes, where each domino covers two adjacent squares. The question is, can you do it? And the way this is normally presented, you give it to somebody and they will perhaps start trying to do it, and then they'll get stuck right near the end, and then they'll sort of make a few adjustments, and then they'll still get stuck, and then perhaps at that point, if they're mathematically inclined, they might look at a 4x4 board instead of an 8x8 board, and even manage to prove by a lengthy case analysis that you can't cover a 4x4 board. And then they'll sort of think, oh my goodness, that was bad enough with 4x4, not likely to manage 8x8. And then after you've tortured them like that for a while, you then show them this picture. It's rotated through 90 degrees simply because that's what was available to steal on the internet. And once they've seen that, this sort of wonderful idea that each domino covers a black square and a white square, and there are more black, which is it? There are more white squares than black squares. Suddenly you have an immediate proof that does the sort of 1,000 by 1,000 case if you want to, just like that. And so it's very easy to understand the proof, but where did this brilliant idea of thinking of it as a chessboard come from? Now, is that an example of an irreducibly brilliant idea that just you have to be a genius human to have, and poor old computers can't? Well, I want to break it down into simpler steps. That's all I really need to do, because if I've broken it down into simpler steps, that shows that it's not all I need to do to prove my case full stop, but it just, in any individual case, if it looks like a pretty good candidate and then I can break it down into simpler things, then it sort of weakens the case that computers couldn't, there are certain things computers couldn't do. So you may object to some of these steps and argue that they are the irreducibly complex things, but I think you can't deny that the steps themselves are simpler than the idea, let's think of it as a chessboard. So this is just a reformulation of the problem. We're trying to show that a depleted grid can't be covered with dominoes, and, well, we'd like to find something, some property that that shape has that no disjoint union of dominoes, so to speak, has. And if we can find such a property, then we're done. Now, if you say this to a typical audience of mathematicians, they'll think, I've got a property. It's the property of being a union of dominoes. And then you say, oh, no, okay. Right, that's not quite what we meant. So what do we mean, actually? We want a property that we can verify. So it's not much use if the property is trivially equivalent to what you're trying to prove. You want something sort of intermediate between sort of trivial in one direction and trivially equivalent to what we want to prove in another direction. So you want some property. Yeah. So how do we go about finding a property? There's a difficulty here. Properties are very, let me just say what it is. properties are somehow meta-mathematical things. You have to describe them in terms of some sentence that says what the property is. And searching through a whole lot of sentences feels like a rather unpleasant thing to do. Just as a little analogy here, if you're trying to solve the p equals np problem, it feels as though thinking about the set of all algorithms is a rather unpleasant thing to do, but there are ways of reducing the problem to using a concept called circuit complexity to a more purely mathematical one about unions and intersections of sets, that sort of thing, which unfortunately is still very, very hard, but at least you feel you're doing maths. So what can we do here? We don't really like to look at the set of all properties, but functions are okay. And if you think about it, again, there's a sort of trivial equivalence between looking for a property that would distinguish depleted grid from unions of dominoes and looking for a function that takes one value on a depleted grid and another value on a set of all unions of dominoes. So, because the function could be 1 if it's got the property and 0 if it hasn't got the property, if you really wanted to. But the advantage of converting it into functions is that we have our ways of thinking about functions that are different from our ways of thinking about properties. In particular, we have nice classes of functions that we that we sort of know about. So once we've reformulated in terms of functions, one option that we have, we don't know that it's definitely going to work, but it's definitely a sensible thing to try, is just work up through the sorts of functions we know. And say, is there a function of this kind that would do the job? Is there a function of this kind that would do the job? So perhaps the simplest sort of function would be a function that took the value 0 everywhere. That's not going to distinguish between anything. So we go a little bit more complicated, and after a while we reach the idea that an additive function would be a good one. So an additive function would be one where it takes if you take any, you assign it to any union of squares, let's say, and if you take a disjoint union of two shapes, then the value on the union should be the sum of the values on the original, on the two shapes. So what property, now at this point we've reduced it to sort of simple exercise. If we're going to go for an additive function, so I'm not saying that idea comes from nowhere, that idea just comes from a short search through simple classes of functions until we hit the additive ones. If we've decided on an additive one, we have the property that we don't want the value that the function takes to change if you add a domino. Now if you think about that, that sort of comes very close to characterizing what the function is. If it's not allowed to change when you add a domino, well, every domino covers two adjacent squares, so it must take minus the value on each square that it takes on the neighbours of that square. And so if you just start at a square, its neighbours are minus that, or say you give a 1 to that square. You don't want to give 0 or it's going to be a bit silly. Give a 1 to that square, then its neighbours will have minus 1s and all their neighbours will have plus 1s, and you find that you've drawn yourself a chessboard, except that black squares turn into 1s and white squares turn into minus 1s, and you've generated the proof. So I claim that each of those steps is not all that clever. So a clever looking idea has been split up into non-clever steps. Just as one tries to do with evolution arguments, you try to split a sort of rather big complex change into lots of small simple ones. Let me just discuss a bit the question of whether computers can do what you tell them to do. So let's consider the following example. This is a whole bunch of patterns that are produced by cellular automata by slightly tweaking the rules. I've put this here just to emphasize that the question about whether computers can do only what you tell them to do is a complicated one because it depends rather on the sort of level that you're talking about. So a program that does this, we haven't told it to produce those nice patterns. We didn't say, I'd like some nice diagonal stripes here, please, and things like that. But so at that level, it's being rather unpredictable. We don't know when we give it a particular rule what the pattern's going to look like, and the only real sensible way of telling is just run the whatever your cellular automaton algorithm is until you see. But at a lower level, it's behaving incredibly deterministically and predictably, and it's just following some very simple instructions over and over again. So you can get unpredictability at one level coming from extreme predictability at another level, which is sort of encouraging because if you believe in a reasonably materialist view of the brain. That seems to be what's happening in the brain as well. At a very low level, the neurons are doing extremely simple things. They sort of fire if they get such and such an impulse, but put it all together in some complicated way, and you get very much less predictable results at a larger scale. But so we can ask ourselves, what would it mean to get out more than you put in? So I want to describe various hypothetical situations that a program might get us in, and just think about how we might react to them. Oh, sorry, I haven't got to that stage yet. So I've talked about unpredictability, and with the cellular automata exhibiting unpredictability at one scale and not at another. And in fact, that's I've been sort of through these points a little bit. What about the difference between unpredictability that's interesting and unpredictability that's boring? So just to give an example of what I mean by boring unpredictability, supposing I were to write a program that worked out the 1000th digit of the square root of 2. I can't predict what it's going to tell me. But on the other hand, I don't sort of feel particularly interested by that unpredictability. I know it's got to tell me something, and it's going to be a digit between 0 and 9, and it goes ahead and works it out. So that would count as boring unpredictability, whereas interesting unpredictability would be something like I write a program to solve maths problems, and I write it with certain problems in mind, and I find to my astonishment that it solves some other problems that I had no idea it was going to be able to solve. That would be a definite example of interesting unpredictability. Indeed, I seem to be jumping ahead. So that would be an example of interesting unpredictability that seemed sort of clever. So here are the hypothetical situations that I was going to say. So supposing you managed to write a theorem-proving program, and you fed it in a problem, and you had no idea whether it was going to succeed, and it did succeed. Now, one situation might be that you then thought about it. You said, well, why did the program manage to solve that problem? Oh, yes, it belongs to I hadn't noticed, but it does in fact belong to a certain class of problems that I already knew that I could do with this program. So that would be sort of nice, but not spectacular in any way at all. Slightly better would be if it solved a new problem that wasn't in one of the classes that you knew it could solve, but on further analysis you realized why the program could solve that problem, and you would add a new class of problems that your program can solve. So that would be a rather better situation. More interesting still would be if the program did manage to solve the problem, but the program was sufficiently complicated that you couldn't really draw any general moral. You couldn't say, oh yes, I see why it managed to solve that problem, and indeed here's a whole class of similar problems that it will be able to solve. The problem, it's conceivable, just as with cellular automata, you might have a program that the only real way of finding out how good it was at doing maths would be just to sort of give it all sorts of problems and see how it got on. So that would be a very much more interesting program if you could do it. Even more interesting would be if it solved a problem but you just simply couldn't work out how it managed to come up with the proof, although you could understand the proof, it was beautiful and everything, but you just didn't know how the computer managed to think of it. Actually, I don't know whether I'd like that or not. But anyway. And obviously a fantastic thing would be if the program actually solved a previously open problem. And even there you can draw certain sort of degrees of interest. So if it solved an open problem, but you then felt, okay, humans should have actually got that problem out. You know, now I see how, now the computer's told me how to do it, I realize I should have managed it. So that would be one situation, and another situation would be if you really didn't feel that, if your computer solved the Riemann hypothesis, then I think everybody would have to admit that that was interesting. However, I'm not claiming that we're going to be able to do that anytime soon. Let me talk about ways of producing cleverness out of where you haven't got it in advance. So there's an analogous, quite a good analogy between mathematical research, or parts of it, and a game of 20 questions. So supposing you played a game of 20 questions, but you did it like this. Somebody was watching you and the person who's got the thing that you're trying to guess. They suddenly have to leave the room for 5 minutes. While they've left the room, you ask 20 questions and you gradually narrow it down to the object. And then they come back in again and sit down. And you say, right, should we get started? And then you say what the object is. And the person sitting there is absolutely astonished. How on earth did you manage to get the answer with just one guess? And of course the answer is that you have not just had one guess, you've had 20 guesses or whatever it is, but you've just not told them about the intermediate guesses. Sorry, let's go back. Now, I would maintain, I think that I'll have a little comment saying that a bit later on, but I would maintain that something rather like that goes on with maths papers. So what do I mean by 20 questions in the case of a maths paper? Well, supposing you're looking for something, as we often are. Maybe you're looking for some complicated set of real numbers that will slot into a proof, and once you've got that set, it will enable you to complete the proof. So there might be some, that's a little bit too simple an example to be convincing, but supposing you want to apply the statement that you've got a continuous function and you want to apply the statement that the inverse image of an open set is open in some rather clever way to solve a problem. So you've got to find yourself an open set to apply it to. So what you can do is things like sort of try out some ideas and see whether they look promising, and if they do look promising, you explore them further, and if they don't look promising, you don't explore them further. So you sort of play, the questions you ask are, what about this idea? Does that get me anywhere? And the problem sort of answers you by either just running you up against a brick wall, or sort of something nice happens, some little cancellation that is rather promising, and you pursue the line further. And so that's what I mean by questions and answers in this case. Now at the very end of all that process, maybe it's a really quite complicated problem, so it's not at all obvious what the open set was in advance, but eventually you find one, and the eventual proof that you write down just says, let A be the set blah, 2 lines, it does the job, end of proof. And somebody reading that may well think, wow, that's good, how did you think of that set? But if you'd actually given the entire sort of, all the things you'd tried, all the sort of questions that had the answer yes and the questions that had the answer no, then they would say, yeah, that was the obvious thing to do, I suppose. And so that's one way of generating cleverness. Play 20 questions, and if you want to generate the cleverness and seem clever to other people, then don't tell anyone about the questions. Another way of having clever ideas is exploiting analogies with other problems. So one of the reasons that we all know that maths problems can be completely intractable but become tractable, which is rather strange. It means that tractability is not an intrinsic feature of a problem. It's more like a feature of a problem relative to the rest of the mathematical universe that people know about. And so one way of having the clever idea that you need is not just to keep slaving away at that problem, it's just for general progress to be made in mathematics until the idea that you need pops up in some easier context and can be lifted over to where you actually need it. And then the sort of general rule is make sure that you hide where your ideas came from. So I'm convinced that a lot of the reason that people have this picture of mathematics as requiring sort of, instead of, people who've done research know that the 1% inspiration, 99% perspiration famous thing is roughly correct, but somehow we sort of feel that's true for us, but for everybody else it's sort of more like 60% inspiration and 40% perspiration, because that's the way their papers look. Okay. What about a different example? So here's a very nice graph. This is the graph that shows that the Ramsey number R44 is at least 18. So this is a graph with 17 vertices, and there are no 4 vertices that are all joined to each other, and there are no 4 vertices such that none of them are joined to each other. There's no independent set of size 4 and no clique of size 4. Now, suppose we ask the general problem. How large a graph can I find that contains no clique of size k and no independent set of size k? Well, if we go back to the beginning of this problem, I think the first observation was made by Turan, who showed that if you take a disjoint union of k minus 1 cliques, each with k minus 1 vertices, then you certainly haven't got a clique of k vertices, because if you've got k vertices, you must have 2 vertices that aren't in the same blob, so to speak. But you also can't have an independent set of size k, because by the pigeonhole principle, you must have, if you've got at least k vertices, then you must have 2 vertices in the same blob, which are therefore joined by an edge. So that gives us roughly a bound of k squared, that's k minus 1 squared plus 1 or something. And if you sit down and try to construct a family of graphs, you will find that it's very difficult to do better than this quadratic bound. But I'm sure, again, this is not news to more than a tiny fraction of people here. There's a much better method, which is not to try to define a graph at all. You just randomly choose a graph. So for each potential edge, you toss a coin. If the coin is heads, you make it an edge, and if the coin is tails, you don't make it an edge. And if you do that, it turns out the number of vertices that you can get is more like 2 to the k over 2. This is actually I used these slides for a different audience, so I will now insult your intelligence, but it's actually insulting the intelligence of a different audience by giving some sort of idea of what k squared and 2 to the k over 2 look like when k is 100. Anyway, you can do vastly better with this random graph. Now there's a sort of, it took quite a while for this idea of using random objects to be noticed, and since after it was noticed, people used it all over the place, and it's now a standard part of the toolkit of anybody in discrete mathematics, and not just discrete mathematics. So it's become a very standard idea, and it's difficult to put ourselves in the position of people for whom the idea was not extremely familiar. But nevertheless, we can see that if you're very used to the idea that if you have to prove that something exists, then the statement you focus on is there exists x such that. It takes a while. There's a sort of block there. It's sort of obvious that if you want to prove that something exists, you should try to find one. So somehow you've got to get yourself out of that block and into a new way of thinking where you just sort of look at a generic object, or you prove that almost all objects have a certain property, and that until you've seen a few examples, you wouldn't guess really that would work. So this is a good example, I think, of an idea that would be a candidate, at least, for being irreducibly hard to find. But one sort of principle I have here is I never see why, if somebody thinks it would be very difficult for a computer to do it, I never see why exactly the same argument won't show that it's difficult for a human to do it. Conversely, if I want to think, how might a computer have done it, I'll think to myself, well, how on earth would Erdős have actually had this idea? Again, okay, he was a very unusual person, we all know that, but I don't think he's so unusual that his brain worked in a fundamentally different way that enabled him to solve a different class of mathematics problems from the rest of us. So one obvious remark to make is that the idea of an abstract existence proof as opposed to a constructed proof was not totally new when Erdős came up with it. So the existence of transcendental numbers is a famous example where you come up with something without actually finding it, although it had previously been found, of course. But another example I like very much is showing that x squared plus y squared equals r can be solved simply by observing that the set of numbers of the form x squared has size p plus 1 over 2, and so does the set of numbers of the form r minus y squared, so those two sets must overlap. And in fact, if you look at the proof that there are infinitely many primes, you don't find an x prime, you find another number and you say either it's prime or it's got a factor and so on, and you don't actually find a prime at all, you just prove that a new prime exists. Having said which, of course, you can convert that into some sort of recipe for a sort of inefficient algorithm for finding the next prime, but or finding a larger prime. Another remark one might make is if you go back to that graph that I showed you with 17 vertices, it was definitely not a union of disjoint cliques. It looked much more sort of spread about. So it's possible that by thinking about that, you might say, well, what would the analog for a lot of vertices be of that graph? Not something all sort of structured, but something rather more random. But that graph had this rotational invariance and was produced using mod 17 arithmetic in a nice way. Or it could be thought of like that, and it helps to analyze it. And that somehow is slightly misleading. That doesn't put you on the right track. And it's conceivable that it could have gone the other way, that maybe Erdős sort of thought, I'm interested in graphs, I've looked at all these problems with the four-color theorem and things like that, and but what does a typical graph actually look like? And if he'd thought that way around, he might suddenly have thought, hang about, they're not going to have large cliques or independent sets. But wait a minute, that so it could have. It's not clear that the problem. I don't know the history here, but it could have just been an observation. He was interested in the Ramsey problem and was thinking about something quite else. Just sort of general curiosity about graphs. Now, I've sort of tried to talk about really fundamental problems, but what about what you might call practical, but very seriously practical problems? So I've already talked about vague ideas. Vagueness is a pretty well-known problem in artificial intelligence. So it would be silly of me just to say it's not a real problem after all. There's plenty of evidence that it is a real problem and that we do need vagueness to do math. Sort of related to that, it's not as cut and dry. Whether a proof is correct or not is a cut and dried matter, but when you're finding proofs, you're not just interested in correctness, you're interested in, you often ask yourself something like, is this statement sort of nice enough to be part of the proof I'm looking for, things like that. So is a computer going to be able to do that kind of heuristic reasoning? I've already mentioned visualization, so that's something that it's not easy to see how you're going to create some. I'll talk about that later, about visualization. But let me address briefly the question of vagueness. So a general principle that I think here is that there are some very serious difficulties in artificial intelligence that are relevant to a general program of trying to solve problems with a computer, but that I would maintain that the domain of mathematics is small enough that there is at least some hope that those problems can be overcome for the purposes of that domain. So, when we're doing maths, well, when you're doing some problem about understanding language, for example, real language, which you might need if you're trying to write a program to translate from English into French, say, you need all sorts of input from facts about the world and lots of very strange aspects of grammar and all those things. Whereas in maths, you've got a rather small, simple grammar. We've just got a few symbols to push around. So it's enough of a smaller domain that it may be that one can deal, that these problems don't manifest themselves quite as seriously in maths as they do in some of these other artificial intelligence domains. So just to give an idea of why I feel that vagueness is something that could conceivably be dealt with if you're just looking at trying to find maths proofs. It's a sort of commutative diagram here that what I've just said here. So a vague similarity that you express in precise language can, at least in many cases, I don't have a sort of general theory here, be converted into, sorry, that word symmetry should read similarity. So it's not otherwise it looks sort of deeper than it was. So sorry about that. So I want to talk about a process of vaguification. So let's take a statement. I want to show how, in principle, Erdős might, because of his knowledge of the uncountability of the reals, of the proof that there's a transcendental number via the uncountability of the reals, that might in some funny way in his brain have inspired him to come up with his argument about Ramsey numbers. I'm not saying again that this is exactly what happened, but just this is the kind of thing that could happen in a computer. So we take a statement like this. And then we'll just gradually make it vaguer by taking precise things and sort of generalizing them. So here goes. Instead of saying uncountably many real numbers, I've changed it just to many real numbers. And instead of only countably many, I've just changed that to few. So that's step one. Where I said some numbers, perhaps I should have said some real numbers, but that wasn't supposed to be part of the vaguification. Well, do we really care about the algebraic numbers here? Let's just make it a bit vaguer. We'll say there are many real numbers, and only a few of them have some property, whatever it might be, and it happens to be algebraic, but let's just forget that and just be a bit vaguer. And then we get that some numbers do not have that property. Actually, this seems to be almost a rigorous argument. The only thing that's not rigorous is I don't know what many and few mean, but it's sort of pretty convincing anyway. Did I really care that it was real numbers? How about just being a bit vaguer still? I'll say there are many objects of some kind, only a few of them have got some sort of property, and therefore there must be some objects that don't have that property. Okay, that's a sort of general principle. The advantage of it is it's very general. The disadvantage of it is that you don't know for certain that any particular instance of it is true. But that's not what we're not using it as a theorem, we're using it as a way of finding proofs. So that's a very important point to make. So what about graphs? Well, let's just vaguify the statement that we're trying to prove here. So we've got a graph with n vertices. We want to show that there's a graph with n vertices that does not contain a clique or independent set. So we sort of say there's a graph. Right, so that was the original precise statement. I've now switched so that that the property of having a clique or independent set has become vaguified to just a property. And now I'm going to vaguify further. I'll forget the n vertices, there's a graph. And I'll vaguify even further. Who cares whether it's a graph? It's just an object. So we want to prove that there's an object that doesn't have a certain property. Now, there was a little sort of quasi-theorem on the previous slide that said that if you've got an object, if you've got many objects of a certain kind and only a few have a certain property, then precisely there is an object that does not have that property. So maybe we can apply that theorem. So we apply it, inverted commas, and then we sort of unvaguify it. So what do we have to do there? We end up having to show that there are many graphs with n vertices and that only few of them have a clique or an independent set. Now, once you've done that, you've had the idea, actually verifying that not very many graphs of 2 to the k over 2 vertices have a clique or an independent set is a straightforward calculation. So the entire difficulty in that problem was having the idea of checking that in the first place. And via this process of vaguification, you can sort of do it using the existence of a transcendental number as your inspiration. Again, it would be stretching a point to say that that's what happened when Erdős did it, but it's not stretching a point to say that something a bit like this could be used inside a computer program to expand what it could do, help it to find analogies, etc., etc. Oh. So I've just said all this. I seem to be underestimating my ability to think in advance of what I want to say. So, so that's what I've just said. I beg your pardon. Now I talked about the evaluative aspect of doing mathematical research. So let's just have one little example of how. So, you might think that a computer would be fine as long as you told it all the definitions that were interesting and all the sort of useful theorems that it might want to use and so on. But it would never actually, how would it decide, hey, this result looks nice, I'm going to formulate that and make it a theorem that I will sort of bear in mind when I'm trying to solve other things, or this definition is going to be useful to me in many contexts, etc., etc. So here was a simple example. Supposing you ask, I won't discuss this in detail, because I think there are more interesting things to move on to. But if you ask how large can the product of two integers be if they add up to n, there are two cases. If n is even, you take each of them to be half of n, and if n is odd, you take one to be n plus 1 over 2 and one to be n minus 1 over 2. So if you work through the problem, you find that you just find that the definition, it splits naturally into two cases, and so the definition of even and odd, if you didn't have it in advance, would emerge naturally from the problem. So what a computer might do in a situation like that, maybe that's not the best example, but would be to say, so those were the two cases there, so that's a potentially interesting definition, put it into some little sort of library of potentially interesting definitions, and if it gets used enough, it goes into a sort of library of definitely useful definitions rather than ones that were sort of useful for one little problem. So that's a typical situation. So if you're trying to solve the previous problem, you find you have a problem because the definition is not there, so you have to make the definition. And a similar thing happens with sometimes if you're trying to prove something that's not true. So this often happens for good reasons. So maybe you're trying to prove a theorem, and it's difficult. There are lots of sort of features of the problem you're not sure whether they're relevant. So you speculate that they're not relevant, and you produce more general statements. You try to prove those, and you might find when you're trying to prove a more general statement that at a certain point you get completely stuck because you need this to imply this. Worse, you find as a counterexample, this doesn't always imply this. But you might also find that this plus some other property does imply this. And so then you've got that property as a potential definition. The statement that this with a certain property implies this is a potential useful lemma, and you can go back and do other things. So gaps, when you're trying to solve one problem, can convert into definitions, lemmas, useful facts that can be then used for other problems. So that provides a way in which, in principle at any rate, computers can make evaluations and possibly learn for the future. Now, one of the last things I want to talk about is going to this point of visual reasoning. So here are three examples of statements where any human will look and say the answer is just obviously yes. So is there a non-negative smooth function? Smooth, let's just say twice differentiable or something like that, not sort of infinitely smooth, otherwise it's a little bit harder, but just sort of, or even I could just go for continuous, it would be okay. So I'll show you what the proofs that would occur to a human look like in a minute. Second question, is there a surface in R cubed? This question isn't even precise enough really, but is there something that would be just like a torus, except it's got two holes instead of one? I'll shut my eyes. Yes, definitely. And what can you say about the intersection of two non-parallel planes? So here are the answers I would give to these three questions if I wasn't writing a paper, let's say. So first answer would be has to be. Second answer would be that, and third answer would be just sort of look at that, and you can see that it's a line. Now, I'm not saying those are rigorous proofs, but I am saying that once I've got those ideas in my brain, it makes it much easier to find the rigorous proofs. I can just somehow sort of convert my diagram into acceptable mathematical proof language, which takes a bit of practice. People don't find it all that easy, but it's certainly a lot easier than finding the proof without the visualization. And it seems like the kind of thing that a computer would have a real trouble doing. So how could a computer do it? Obviously not using pictures of the kind that I had before and sort of looking at the pixels and trying to work out what they represent and so on. That's going to be completely hopeless. Another idea, a circle, maybe a computer could understand a circle as the equation x squared plus y squared equals 1, but that somehow seems too specific, too Cartesian, and who says it was a circle of radius 1 centered at the origin, etc. It just doesn't feel right. That's not what a circle is somehow. So this is just, I do think this is a serious problem that I don't claim to have got anywhere with, but just this is what I think that a solution or a way of getting around the difficulty might conceivably look like. So I'll give some examples in a minute, but I think one might want to create a sort of something that's intermediate between what we do with our normal symbolic reasoning and what we do with pictures, some sort of descriptions of pictures that capture their essential features and not their inessential features. So let's have some examples. Some sort of computerese version of what I've just written here for the first question. Instead of giving an equation or giving an actual diagram, you just say, if I were to write that and send it in an email to you and ask you to draw a picture, you would draw basically the picture I intended. And any differences between the way people would draw it would tend to be differences that I didn't care about. So that sort of shows, that's meant to be a kind of proof of possibility. It is that such things do exist. Similarly, if I want to describe how to produce a two-holed torus, I could say it like this. I sort of make myself a figure of 8, I blow it up, and roughly speaking take the surface of that shape and maybe smooth it off if I want it to be smooth. And finally, this is a bit odder because it's more as though I'm just producing one example of a pair of planes that intersect in a line, and then just sort of arguing, well, obviously that's true for all pairs of planes. But it sort of is obvious once you've got one example. I think what's going on there is once you've got one example, you can sort of see that you can distort it to produce any other example. Oh, I just accidentally pressed a button, but my time is nearly up. So let me just talk about, timeline is not quite the right word, but sort of progress line. Different stages that one might reach in the general project of creating programs that can do maths. So the first step that I think really there's no reason to suppose is not going to be possible. How soon, I don't know, but I would be surprised if this hasn't happened within, say, 20 or 30 years. We have a program that was very good at finding routine consequences of things. So any problem that you say, well, obviously, blah, 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 the computer also finds it obvious. And it seems to me that that's because the reason we find some things obvious is that we have got a little mini algorithm in our brain that we use in a certain context. We run it, it produces the answer, no unexpected snags, and so we just have to work out what that algorithm is and program it. And that would be a lot of work, but possible. Now, imagine if you just had that, supposing that was where the whole thing stopped, you could still do amazing things with it, like you write a paper. When you write a paper, you don't want to put in all the details because the people who are reading your paper will be able to fill in quite a lot of stuff for themselves. But maybe a beginning student wouldn't, and maybe there's a chance that you've introduced an error by not putting in all the details. If you've got a computer program that can fill in, can work out routine consequences, they can just check that the details that you didn't put in do actually work. That would be an amazing resource. There'll be many other things. So what's routine for one person is not routine for another. So if you're doing research that's very slightly out of your area, you could say, well, is this a known fact? And they say, well, it follows easily from these two known facts or something like that, and you wouldn't have found that yourself at all easily, but the program can find it. So that would be one thing. A whole stage better would be if you can teach it to do clever things, that you teach it methods that you yourself were perhaps taught at some stage or maybe thought of. And that once they're thought of, it makes a whole lot of problems easier than they were before. A whole sort of complete game changer would be if the program could learn from its own experience. So in the way that I described before, that humans can. If humans solve a few well-chosen problems, it enables them, it somehow gives them the ability to solve a much wider class of problems. And if the program could do that, that would be fantastic. But if it could also recognize interesting problems, then you'd get the absolute dream of a program. You stick it in your computer and you go off and come back in a year's time and see what it's proved. You know, it's sort of developed a whole lot of theories and perhaps it's proved the Riemann hypothesis and things like that without any input at all from humans. But yes, that's probably a way off. And I'll stop there.
Time for one or two quick questions, if anybody has one. Yes.
Thank you, Tim. Wonderful. I'm not in a position really to agree or disagree, but I'm thinking about, at one point you used the term think of a computer. I'm not criticizing that, I'm just noticing that it was a nice slip. Another time you used understand, almost ironically, that it wasn't doing that. It made me think of the following way of squeezing a question into an issue, is this. So we've evolved a computer, we human beings. Why hasn't the computer evolved before us and evolved us instead? Silly science fiction question, but what I'm trying to get at is how the criteria of identity of our yielding a new identity, namely a computer, is always going to be parasitic on what we can do, but subordinate to it. And so a silly question might be, why didn't the universe evolve a computer first and then evolve human beings? So I'm playing around with that, trying to get at the center of what is it to have consciousness and think, which computers don't do, without thinking of the future.
I tried to avoid that last issue of whether computers could be conscious. But I don't know. I mean, I think my instinct would be to say the universe did evolve a computer, and here we are. But it's just a rather more complicated computer than the ones we have here, which are sort of playing a game of catch-up. Otherwise, I'm not quite sure what else to say on that.
I just want to make a comment kind of on the question in the title and the whole, like, everything around this topic, which is, it seems very, the unsaid thing is that it's us against them, that we're the mathematicians and we need to defend our jobs against the computers, and let's comfort ourselves by making sure that they can never do what we do valuably. But from someone, like, I use computers all the time to help with mathematics. Like, I use computers in my mathematics. So it seems like all of the things that they're good at and all of the things that you, like, you know, finding routine consequences and even learning from experience, things that would make them even more autonomous, would still enable me to treat them entirely as tools and would just make me a much quicker and faster at doing myself. And I think we should turn, like, instead of focusing on what computers can't or can do, how can we use computers more productively to do more mathematics and enrich the whole world?
Yeah, I take a supremely selfish view about this, which is that within my lifetime, I expect computers, well, the best that will happen is that computers are an extremely useful aid to doing mathematical research, but don't take over. And then sometime, sort of 30 or 40 years after I'm dead and gone, mathematics as we know it no longer exists because you just type something into a computer and it gives you the answer. It doesn't just give you the answer, it gives you a beautiful explanation and all that sort of thing. It's just maths has gone the way of big numerical calculations, which we no longer ever consider doing by hand. But there's this sort of glorious period before it disappeared. It's unbelievable. All the hard work's taken out. Well, that's an exaggeration, but.
I think we should probably move on, so maybe that's a good moment to stop and we can continue the conversation over tea. So let's thank Tim again.